Today we'll be learning about GCD, how to calculate the GCD of two numbers using C++. Suppose you have a number 20 and 28. Let's see here for better understanding. Find the GCD of 20 and 28. So how we are going to find the GCD? First we are going to factorize this 20 into individual prime numbers. It will be 2 times 5 times 2, and let's factorize 28. It will be 7 into 2 into 2. Now we see the highest number over here is 4. This is 2 into 2 and this. So we get the highest number as 4. So this is the GCD, also called HCF, highest common factor. So how will you code this? So it's very simple. You have to, we know that GCD of the factor, you have to know that the common factor is 1 for every case. In every case common factor is 1. Suppose 3 and 5, their GCD will be 1 because um, they have only one common factor, that is 1. 3 into 1, and for 5 it's 5 into 1. So the common factor is only 1, so that's why the common factor is 1. So what you want to do in coding is for coding we need to iterate from 1. We're gonna iterate from 1, and then we will go till the max of either. So this is the function GCD of AB. So we will go until the max of A or B, and we're gonna increment it. This will be our for loop, and inside the for loop we're gonna write we're gonna check that whether A percentage I equals 0 and A and B percentage I equals to 0. If this condition is met, then we will say that GCD is equals to I, because we need to check the common factor. So we checked it and we have to return GCD. First we need to initialize GCD as 1. As you can see here, we are checking whether I factorizes A or not, and also simultaneously checking that whether I is factored by B is factored by I or not. So we now see that these two are factored, so we store the value of I in the GCD variable. Now at the end of the loop, the last updated value of GCD will be the highest, because we are going from 1 to the max of A and B. Actually we can do min of A and B. That will be much more better. This is the basic algorithm. Now let's run the code. So here is the code for the GCD. This is the brute force approach. We iterate from 1 to the minimum of either A or B, and then we check whether the I is dividing A and B together. If they're dividing, then we store the value of I in the GCD variable, and after the iteration is complete, the maximum value of I will be maximum value of I, which is also the common divisor of A and B, will be stored in the GCD variable, and we will get the desired GCD. Now let's see certain issues, I think. Okay, yes, the code runs properly. Now if I The code works, but there is a runtime error because I'm using a brute force approach. So let's fix this by um, so let's fix it. So here we are using we are going from 1, we are going from 1 to the min of a and b, but instead what we can do is we can go from min of a and b to 1, because the GCD always lies at GCD is always the greater number. So instead of the i's value should be greater in the beginning only. So if we see a common, we see the we see two greater, we see dividing a and b simultaneously, then we just then we just return the GCD, return the value of I into in the GCD right away, and hence we can reduce a bit of computation time. Well, the complexity is still big O of n because we are big O of min of a and b, because we are still iterating through the number. But using this approach, the algorithm will be a little bit better. So let's see. So here we are. So we start the value of I with minimum of a and b, and we go until I, and then we decrement the value of I. So then we again check whether I is dividing a and b simultaneously. Then the GCD is equals to I, and then we immediately break it because we know that GCD is basically the greatest of the divisors. So we will be getting the greatest of the divisors at the first if condition itself. So now we break it and then we return the GCD. Now let's see whether it compiles. The code compiles, and let's see by submitting. Still we are getting a time limit exceed. So we need to think of a better approach. Now the better approach is basically Euclidean algorithm to find the GCD. So Euclid has stated that GCD of A and B is equals to GCD of A minus B comma B, given A is greater than B. A greater than B. Okay, this is the Euclidean algorithm. Suppose let's take an example. We find the GCD of 15 and 20. Now what we're gonna do is you can write it like this: GCD of 20 minus 15, because 20 is the bigger number, and we write the smaller number here like this. So it basically comes out to be 5 comma 15. Now again here we can write GCD of 15 minus 5 comma 5, because 5 is the smallest number among the parameters. Now we can write GCD of 10 comma 5. Now again we can write this is GCD of 10 minus 5 comma 5, which is equals to GCD of 5 comma 5. Now again we write GCD of 5 minus 5 comma 5, which gives GCD of 5 0 and 5. So whenever we get the first 0, this is the time we stop the algorithm. See, we get the 0 over here, so we stop the algorithm, and so we got to know that 5 is the GCD. Therefore we can write that GCD of 15 and 20 is equals to 5. We can, let's see the algorithm in the code. So here is the code. We first we initialize a variable GCD1, and we get the largest of the two number of AV. We store it in the variable large, and the smallest of the number B, number A and B in the small variable. Now we check whether the small is not equal to 0, because in the algorithm you can check that here in the algorithm itself you can check whenever we got the 0 over here, initially we stop the algorithm and we return the highest number, that is 5 over here. So similarly, we have to check whether the small number is not equal to 0. So the loop runs until 0 is reached. So we basically do the same thing in the algorithm I explained previously. Large is equal to large minus small. Over here you can see I am subtracting the large number by the small number. So I subtracted, and in case you can see that sometimes a large number is getting in the large number is getting smaller, then we shift it to the right side. Over here you can see that this is 5, but since this is smaller, we shift it in the right side and we keep the larger number on the left side. So this is the reason I'm swapping the large and small numbers, because whenever I see that the large variables number is getting lesser than the small variables number, then I immediately swap the large and small so that it maintains proper balance. And it is after the iteration reaches the after the iteration reaches to the small value of 0, then the algorithm stops and we can conclude that GCD is the largest of the number, because as you can see here, this is the smallest number, this is the largest number. So GCD is basically the largest number. So we store GCD. We, so we store the large number in the GCD variable and we return it. Now let's compile. It's compiled perfectly. Now let's submit. And the test cases are passed successfully. And another way to optimize this algorithm is, let's see, we can optimize further. In the previous slide, you saw that we found the GCD of 15 and 20, but we just subtracted for a long amount of time, right? But instead of subtracting, instead we can write that GCD equals to 20 percentage 15 comma 15. So if we write the remainder, then it comes out to be GCD of 5 comma 15. Okay, now again we can write this as 15 percentage 5 comma 5. Now again we can write this as 15 comma, we can see the remainder is 0. So now we can get that this is the GCD. GCD is 5 is equals to 5, because 5 is the largest number. And why did this work? Because as you can see, if I keep on subtracting 20 minus 15, which gives me 5. Now if I subtract 5 minus 5, it gives me 0. So instead of um, subtracting the number by multiple times, we we can just divide and get the remainder, because that's much more efficient. So after we get the remainder, uh, we can continue the process further. So let's see what changes we can do in the code. So in the code we can write, instead of minus we can write percentage, so that it gives us the remainder. Perfect. Now let's submit. I'm hoping it will be submitted perfectly. It's perfectly submitted. Now let's analyze the time complexity of this. Are subtracting a number, say let's say 20 minus 15, for how many times? For it depends on the smallest variable, like this 15. So a minus b. So we are subtracting a number by b times. So if we subtract the number by b times every time, then this b is basically a variable. If I subtract the number by 10 times, then we can say that case variable is 10, and for each and every time I subtract the number by 10 time by number 10, then I can say the time complexity will be log base 10 n depends on the number, but here we do not know the value of k is a variable, so we can say that let's, instead of k, we write it as psi. So uh, the base of this log will be phi, and then it will be log n. So the tc will be equals to big O of log n, and the space complexity is equals to big O of 1, because it's constant, we don't need to use any space. That's